Okay, so dealing with logic, we have to start by defining some of the very basic constructs that we're going to use here. Statements being the most basic. And then we're going to talk about quantified statements as well. So we may all understand the concept of a statement, but let's formalize it. Let's make sure we're all on the same page with it. A statement is a sentence that is either true or false, simply put. Asking a question is not a statement. Saying there's other certain things that are not considered statements. But let's see a couple examples. London is the capital of England. That's a statement. Is it a true statement? I believe so. Yeah, I think London is the capital of England. William Shakespeare wrote the television series Modern Family. Let's make it more fun. William Shakespeare wrote the television series Game of Thrones. No, it was written by a couple of hacks who ruined the last couple seasons of that show. But the books were written by George R.R. Martin. Is that a statement? Yeah, I'm making some kind of claim, or I'm trying to say something is a fact. It's not a true statement, though. It's clearly a false statement. What's interesting, though, is if you like Game of Thrones, George R.R. Martin takes a lot of his story from actual English history, specifically the Wars of the Roses, which are covered in Shakespeare's King Henry VI, parts 1 through 3, as well as Richard III. So it's pretty interesting. A lot of all the deception we see on Game of Thrones and all the Machiavellian scheming is taken straight out of Shakespeare and actual history as well. So it's kind of interesting. So these are statements. They're not both true, but they could be true or false. What is not a statement? Titanic is the greatest movie of all time. That's definitely false, but even so, it's an opinion. It's an opinion. This is another movie, and that is my favorite movie of all time. It's still an opinion. In this class, my opinion is always correct, but in general, an opinion is not exactly a statement. It's not exactly a statement. It's just a thought. Read pages 23 through 57. That's definitely not a statement. You're just commanding someone to do something. So a statement is not the same as a sentence, something that ends in a period or something like that. A statement is a sentence that has to have a true or false value. We may not be able to establish the true or false value, but we have to say it. And then a bit of a philosophical conundrum. If I start losing my memory, how will I know? Well, again, maybe that's an interesting question, but that's not a statement. As a question, it's pretty much not going to be a statement. So we have to be able to assign true, false values to it. Now that is deceptively simple. That's deceptively simple. What we're going to see later on is that we are going to create larger statements out of simpler ones. We're going to create what are called compound statements using words like and, or, and then technically the word not. That creates something that's a little bit more compound. Now, just like in math, if you're talking about straight up numbers, values, you use variables. X and Y are usually the two most popular variables. Those things represent unknown numbers. In a similar manner, we're going to use letters to represent whole statements here. Now, these statements may be known, but whenever we're doing some of the operations we're about to be doing with these statements, it's going to be a pain in the butt to have to constantly write the entire statement, especially if it's particularly wordy. So what we're going to do is we're going to use P's, Q's, R's, maybe we'll see an S, and we're going to simplify our lives. We're going to start using symbols to relate and compound those statements together. So for instance, we'll let the statement P be the statement London is the capital of England. Q can be that William Shakespeare wrote Modern Family. Is that show even on the air anymore? Is it? I think it's off the air now. But it was an all right show while it was on. So a statement is a sentence that must be true or false. What we're going to investigate then is something called the negation of a statement. The negation of a statement. Now, if you start with a true statement, the negation is the statement which takes the exact opposite sentiment of your original statement. It takes the opposite stance. So if I say my statement at P is London is the capital of England, the negation of that is London is not the capital of England. It's just the statement that takes the opposite stance. And because it takes an opposite stance, the negation of a true statement must be false. And the negation of a false statement must be what? True, exactly. They take opposite stance, so whichever the truth value of one, its negation will have the opposite truth value. It must. So again, all of this is seemingly simple. All of this is seemingly very simple at the moment. It's going to, of course, ramp up in difficulty. Now, here's the thing. How many of you said, Josh, I signed up for a math class. Math classes are supposed to be numbers, and you do calculations, and you punch numbers into a calculator, and you learn formulas, and you plug numbers into formulas. How many of you are like, this is not math? You can be honest. You can be honest. That doesn't. With the stuff we did in chapter 2 about set theory, how many of you looked at that and you said, this isn't math. This is a bunch of weird nonsense, right? Well, actually, believe it or not, that is math. In fact, things like computations and number crunching and formulas, all of that really stems from some of the larger math that we're learning here, from the chapter 2 material over set theory. And then from this, the chapter 3 material over logic. It turns out that when you go down the rabbit hole with mathematics, you have to get into things like this, which are much more abstract, which don't have hard numbers associated with them. And there's nothing you can do about that. That's just, and I would argue that this is actually what math is, what we're learning here, than number crunching. The good news is if you love number crunching, we're going to get right back into it once we get to the next chapter, which is we're going to skip to chapter 8. And then it's going to look like a really very math class. It's going to be all number crunching pretty much through the end of the semester with some other concepts touched in. So you may very much like this stuff. You may like all this stuff concerning logic because all of this builds the foundation for the later mathematics we do that looks like number crunching. That's the key. We need logic to be able to do this. Anywho, if you have the statement, Shakespeare wrote the television series Modern Family, then the negation of that is pretty obvious. Shakespeare did not write the television series Modern Family. Now, you can reword that in a number of ways. You could say the author of Modern Family was not Shakespeare. You could say that. You can re-express that in a number of different ways, but all of them take the basic sentiment. They are the opposite of the original statement. If you start with the statement, today is not Monday. Let's do this one. The opposite sentiment, aka the negation, would be that today is Monday. Pretty simple. You take the opposite statement. It doesn't always mean you put the word not in there. Sometimes it means you take the word not out. This is the next one. It is not true that today is not Monday. Well, wait a minute there, Pilgrim. If you're using a double negative like that, you have not and then not again, you really just, that's two negatives make a positive. So I'm not even taking the negation yet. All I'm doing is saying that today is Monday. That's equal to that. It is not true that today is not Monday. That is the exact same thing as saying that today actually is Monday. It's kind of silly. It's kind of just playing around with words and semantics. Yes, I'll grant you that. Thus, the negation is that it is not Monday. Pretty silly. This last one, today is Monday, is the same as the previous statement up here, the one in black. So again, it's pretty simple, straightforward stuff, and then all of a sudden we're gonna throw some extras into it. We're gonna learn that there's not only the negation, there's the words and, there's the word or. We'll talk about if-then statements as well in logic. And as you can see, we're going to use a lot of symbols. We have to. So we use this little squiggly line. We use the little squiggly line. It's called the tilde. That's going to be our symbol for the negation. If you see a tilde before a letter, you're actually taking the negation of the statement that letter represents. So the tilde. So P is the statement Shakespeare wrote Modern Family. Q is the statement today is not Monday. So the first one, Shakespeare did not write the television series Modern Family. This is the opposite sentiment of that. Thus, if the original is P, the new statement we formed here, the negation, is not P, tilde P. And that's literally read not P. That's exactly how you say it, not P. Over here, not Q. Well, if the original Q is the statement today is not Monday, the opposite sentiment of it is that today is Monday. So even though the word not, you won't see it here. That's okay. It's still the opposite sentiment of the original Q statement. Thus, this thing down here, not Q. That's what that tilde means, not Q. So we take the opposite sentiment. So pretty straightforward. Next up, we can talk about quantifiers. Quantifiers. Now, a quantifier expresses a quantity of something. Now, we're not necessarily in logic going to use actual numbers here. We're not going to say 23 poets or 74 math books. We're not quite going to do that. We're going to use some real general terms. We're going to use words like all, some, no, or none, things like that. So if we say that all poets are writers, all poets are writers. Well, how many of you would say that's, first of all, that's a statement, right? All poets are writers, sure. How many of you would argue that that's a true statement? Yeah, I would say so. I mean, unless you try to get real weird and say a poet can be someone who draws pictures, which, I mean, you're stretching the limit at that point. But unless, if you're clearly talking about a poet who writes poetry, yeah, they're probably a writer. So that's probably a true statement. When I use the word all here, I'm saying that if I pull someone who's a poet, let's say T.S. Eliot, they're automatically also what? A writer, exactly. Now let's go the other way with it. Let's say I pick a writer. How about, who's a good writer? How about Stephen King? Stephen King, very famous horror writer. You've guaranteed you've seen a movie based on a King novel. Would you say that Stephen King is a poet? He may have written some poetry at some point, so I won't rule it out. But generally speaking, you're not going to call Stephen King a poet because he writes prose, which is non-poetry. So someone who is a poet is automatically a writer, but someone who's a writer is not automatically a poet just from this statement here. That's a huge distinction. That's a huge distinction. In fact, we're going to make that distinction so clear with a picture. If all poets are writers, then that means the set, oops, no. then that must mean that the set of all poets, which we will represent with this circle, must completely lie within the set of all writers. The set of all poets must completely lie within the circle of all writers. So if I take a single person, let's say I select T.S. Eliot with that green dot. Well, T.S. Eliot is in the poet circle, thus T.S. Eliot is a poet. T.S. Eliot is also within the larger writer circle. So if I want to say all poets are writers, this is a perfect picture to represent that, because the entire set of poets is within the set of writers. Didn't we learn something in chapter 2? What was that called? The subset? You guys remember the subset in chapter 2? Wait a minute. This is just saying that the set of all poets is a subset of the set of all writers. If I created a set that contained every poet in existence within that set, it's going to be a huge set. But if I did that, and then I also took the set of all writers, the set of all poets is a subset of the set of all writers. If this statement, all poets are writers, is a true statement. That's pretty cool. From this little 4-word sentence, I can relate this back to chapter 2 subsets. I can think about it in terms of this picture here. This is kind of like a Venn diagram, but where one thing is a subset of the other. And then if someone is in the writer's circle, they are not necessarily in the poet circle, are they? You can have people who are writers, but not poets. And the example I used was Stephen King. I think he uses PH. Stephen King. That's a person who's a writer, but not a poet. Shakespeare would be both. So Shakespeare, because Shakespeare wrote, many sonnets, 90-something sonnets, I think, somewhere in that ballpark. So Shakespeare would be someone who is both a poet and a writer. Thus, he would belong in both. Probably the most famous writer in the English language. So all of this just from a simple little 4-word sentence. That's kind of cool. What we're going to learn is that everything we're going to cover in chapter 3 is going to be, it was already covered in chapter 2 under a different title, under something related to set theory. Yes? Yeah, so Eliot wrote both poetry and he wrote regular fiction, right? Or he wrote things. But you can have writers who are specifically not writing poetry. Poetry is a type of writing, but there's also the field of prose, which is just kind of regular speak. So J.K. Rowling, who wrote Harry Potter, she doesn't write poetry really, she writes prose. She writes in that form. Does that make sense? So yeah, so within the field of writing, you have poetry, but then you also have other types of writing that can exist that are not poetry. So yeah, this definitely is very interesting. Prose and poetry are generally the two forms of writing. Some people are bigots. Well, whether or not that's a true statement, that is still a statement. The word all is pretty easy to deal with. If I say all poets are writers, that's actually pretty straightforward to deal with, because then if that's a true statement, there's no exceptions to it. There's no gray area. When you use the word some people are bigots, what that really means is that there's at least one person out there, at least one human being who is what? A bigot, right? There's at least one. When you say some people are bigots, there's got to be at least one, or else that statement's false. If it's the case that there's absolutely no one on the planet who is a bigot, and I don't think that's the case, but if it was the case, then really you can't say that some people are bigots. So the word some is a little bit different. The word all makes us think of a subset. But the statement, some people are bigots, which is not a good thing to be at all, that makes me think of a more traditional Venn diagram. That makes me think of a traditional Venn diagram. You have the set of people. You have the set of bigots. And unfortunately, there's going to be an overlap between them. The people who are in this middle section are people that are bigots, that are both bigots and they're human beings. Now, once again, what would be in this section over here, this section that's not shared between them, just completely on its own? I guess if there are animals or aliens or something, then they're not human beings, but that's kind of silly. But when you see the word some, you should be thinking of a more general Venn diagram. So just a few interesting cases. How about the statement, no math books have pictures? First of all, is that a true statement? Definitely not. We can easily find math books that have pictures in them. So it's not a true statement, but just for the case of pretend, just assuming that it's true or pretend like it's true for the moment. If no math books have pictures, there's a couple interesting logical things we can think of. The obvious one is if I pick up a math book and this statement is true, if I pick up a math book, I can go through that entire thing and not find a single picture. I would argue that almost every math book on the planet has pictures, or at least some diagrams, pictures, tables, graphs, things like that. What it also means is that if I pick up a book and I can see that the book has pictures in it, that means that book must not be what? A math book, exactly. If I pick up a book that has pictures, and if this statement is true, and I know it has pictures in it, that can't be a math book. It can't possibly be a math book. Of course, the statement isn't true, which brings us to another point. If you have a statement like this, no math books have pictures, and you want to prove that that's wrong, all you got to do is go find a counterexample. You just have to find a single math book, open it up, and find a picture in it, and you've proven that statement wrong. That is a very common, I don't want to call it a trick, but it is a very common strategy that's used to prove things. Oh, you're trying to make this ridiculous claim? I just got to find one counterexample and you're cooked. You're done. But if you want to think of it as a picture, no math books pictures. Let's assume this is true for the moment, just for argument's sake. Then if I draw the two circles, well, I certainly couldn't put one circle inside the other. They should have nothing in common. I shouldn't draw the Venn diagrams overlapping because they should have nothing in common. I should draw the circle. This is my circle that has all my math books in it. And this is my circle. This would be all books with pictures. They should have nothing in common, no overlap. They're completely standing on their own. Of course, this isn't actually a true statement. So we can pretty clearly establish that. So just from a few very simple cases, we can relate all of this to set theory. What you would say in set theory is if you're making this statement, then the set of all math books and the set of all books with pictures, their intersection is empty. That's what you'd say. If I tried to do intersection between them, there's nothing in common, so we'd use the empty set to express that. So very interesting stuff. Pretty interesting. In fact, I'll say that. Let M be the set of all math books, P be the set of all picture books. if the above statement is true, then if I intersect the set of all math books with the set of all picture books, I get the empty set. There's nothing in common. The intersection is empty. So some pretty cool stuff. So when you say something like no X is Y, you're making a pretty large statement, something that's a little bit larger than you think it is. It's also pretty hard to make that statement. There's a lot of statement. I mean, you have to prove it, and some things are not easy to prove or establish. So you have to use other types of reasoning. So here are the four statements, the four basic types of logical statements. So let's just look at the first column here. There's only four basic types of statements. We might use some fancy wording to write those things in different ways. We might do that. You might read a newspaper article, or, well, what's a newspaper? You might read an article online, you might read a story online, and it'll make a claim, and it won't write it all A or B, but the claim will be basically that exact same thing, just with fancier words put to it. So all A are B, some A are B, no A are B, some A are not B. Those are the four basic type of quantified statements that we're going to make. So now let's investigate each one step by step. That first one, all A are B, is equivalent. It is the exact same thing as saying there are no A that are not B. Hold the phone. Wait a minute. If I say all poets are writers, let's get that picture in our head. Anyone you call a poet is automatically also a writer. What that means is that I cannot go out into the world and find someone who's a poet that is not also a writer. It sounds silly, but it's almost like the double negative. There are no poets that are not writers. So let that sink in for a moment. These are equivalent ways to express the same statement. Let's look at the next one. Some A are B. The only way for that statement to be true, that some of category A is also category B, the only way for that to be true is if there's at least one thing in category A that is also in category B. So if some people are bigots, if some people are bigoted, the only way that statement can be possibly true is if I can at least find one person who's a bigot. If I can't do that, then that statement's not true. Thus, these are logically equivalent. Some A or B is logically equivalent to there's at least one person who is also B. How many of you would say this is a little bit confusing now? It's starting to get a little bit confusing. How many of you would say it makes sense? It's generally clicking. You guys would say that? Okay, good to hear. It is so different because, again, you're walking. I'm going to say this probably 14 more times, so I hope you're ready for it. You're walking into a math class. You're like, I got this nice fancy calculator. I'm going to be multiplying stuff and adding stuff. And then we're doing this business. And you're like, what is it? Huh? You're like, huh? No, we're not multiplying crap right now. That's okay. This is forming the foundation for important kinds of mathematics that we do. But I promise you, once we get to chapter 8, this is going to look like a completely different class. We're going to talk about calculating your taxes for the year. We're going to talk about computing the monthly payment you'll make if you buy a house. So we're going to get right back into number crunching and all that. How many of you are excited about that? Okay, a little bit. Yeah, I can feel you on that. You go into a math class, you expect a certain thing, and when it's not that, it can be disappointing, even if the new stuff is actually kind of interesting. You know what I'm saying? You have an expectation in your mind. But anyways, I'm rambling. If you have the statement no A or B, nothing in category A belongs in category B. If you say that statement, another way of putting it is that all things in category B, or excuse me, all things in category A are inherently not in category B. Again, it sounds a little confusing, but if nothing in category A is in B, so let's see. No common colds are fatal. I mean, I would argue that's not true, but assuming it's true, that no common cold will end up being fatal. That's the same as saying of all the things in the common cold set, not a single one of them belongs in the set of things which are fatal. So no common colds are fatal is equivalent to saying all common colds are not fatal. Again, I hope this isn't confusing because it seems simple, but when it comes down to it, sometimes you have to pause for a second and think about it. You got to turn on the heat a little bit. And finally, if you're saying that some things in category A are not in category B, it's kind of weird, but what you're saying is that not everything in A is also in B. So some students don't work hard. If some students don't work hard, there's at least one student out there who doesn't work hard. Now, hopefully that's not you, but I would agree that that's certainly a true statement. How many of you kind of in middle school, high school, you didn't always give your best effort? Be honest, be honest. I think that's true of everybody. I certainly was true of me. So it's not to say you can't work hard. It's not to say you don't have the ability to do it. It's just saying you're not doing it. You're not trying it at the moment. So if some students don't work hard, then there's got to be at least one student out there not working hard. And thus, not everything in the set of students works hard. Not all A or B, not all students work hard. Does that click? Good. I hope it clicks. If it doesn't, please stop me. I can try to re-explain it in a different way. But it's just kind of going from understanding the words and their meanings behind them. What's really interesting, and I am going to go on a little bit more of a rant. Over the last century, really, especially since like the 1960s with the Cultural Revolution and all that, there has been a great rise in an artistic movement called postmodernism. How many of you have heard of that? How many of you have heard of modernism? Modernism came about in the early 20th century as a response to the horrors of World War I, and then again into World War II. Modernism took a very not sinister, but a very sarcastic look at the truth of things, and it established postmodernism, and postmodernism is really out there. Postmodernism basically says that everything is absurd, that words do not have specific meanings, and specific meanings are not necessarily tied to specific words. Now, that doesn't sound particularly profound, except that it has completely set the foundation for a lot of fairly ridiculous things. Now, postmodernism isn't all bad, but I think there's a little bit too much of a good thing can be bad. And so what postmodernism has done is it has attempted to erode away the principles of logic. And that's a very bad thing, because almost everything we do, our laws and legal system are based on logic. They must be. And to erode away the very foundations of that is to potentially take away lawfulness in a country that lives under laws and doesn't murder each other and things like that. So postmodernism, that's a very simple nutshell of it. But postmodernism would attempt to say that all of this is nonsense that I'm teaching you today. And I just can't believe that. There's so many good things that has come out of logic, even if we don't know about it just yet. So anyways, that's just an interesting idea. Don't let postmodernism try and affect you. Pretty much anything you see on TV or movies today, if they're popular kind of stuff, almost all of them have been touched by postmodernism in some way as an artistic movement. And while it might make for some interesting TV, It doesn't necessarily make for a good legal system or things like that. Okay, so now we have the four basic statements, all A or B, some A or B, etc. We have the four basic statements. We have an equivalent way of expressing those same statements. What we're going to find is that these four basic statements already have their negations implanted there. The statement all A or B, let's put on our thinking caps. Let's put on our thinking caps. Let's take the statement all poets are writers. It's one we're already comfortable with, that we've already been dealing with. Now I come in, I walk into the classroom, and I'm going to do this. So if you're in Zoom, I'm going to literally walk into the classroom again. I'm going to walk into the classroom. Hi, everybody. How are we doing today? Is it a wonderful day? It's starting to get a little bit warmer. It's going to get cold again later this week. I walk into the classroom, and I say all poets are writers. What would you do to disprove me? What would you offer as evidence to say that I'm wrong? Well, maybe if you could find a poet that's not what? A writer. If I walk in, I say all poets are writers. All you got to do is find one poet that's not a writer, and you've disproven me. So you have to be careful. You would think that the opposite of all poets are writers, you would think the opposite of that is no poets are writers. But that's not the case. The opposite of all, you simply have to find one thing that is not true. One counterexample, if you will. Thus, the opposite of the statement all A are B is the statement some A are not B. These are negations across the diagonal like that. It's very tempting to think that the opposite of the word all is the word no, but it's not. The opposite of all is to simply find at least one counter example. So again, if I walk into the classroom and I say the statement, all math books have pictures in them. The opposite of that is not to say, no math books have pictures, because that's just as difficult to establish. The opposite is to just find a single math book that doesn't have pictures. There could be others that do have pictures. Then if I take the statement some A are B, you're tempted to say that the opposite of that is some A are not B. That's not going to be the case. If I try to say that some comedians are TV actors, the opposite sentiment is to say actually no comedians are TV actors. That's the only way to disprove that. Now it's ridiculous. There are certainly some comedians that act on TV. So that might be a true statement. But to take the opposite stance, I have to really go far. I have to go the extra mile for that stance. So the opposite of the some A or B is to say that no A. Again, that does not sound particularly profound. It seems like a simple concept, but it's not as simple as it first appears. I promise you, you're tempted to say that the opposite of all A or B is no A or B, and you have to fight against it. You have to think about it logically. So here's some of the pictures we already kind of established. If you have the statement, all writers are poets, the negation of that is to just find some writers that don't belong in the poet circle as well. That would essentially disprove that first statement. So pretty interesting ideas. I want to give some more examples of this, because I think this is very apt. What if I walked into the classroom today and I said, all TV shows, who's a famous actor? Who's a famous TV actor? No, let's do movies. I think movies are more common. Someone give me your favorite actor. Who? John Wayne. All movies have John Wayne. I love that your favorite actor is John Wayne. That's so cool. I like that. John Wayne. I love John. So you like it when I do my pilgrim routine? You like that? Maybe you don't. I don't know. So I walk into the classroom and I say, all movies have John Wayne. How would you disprove me? How would you disprove that statement? That? Show you a movie that what? That doesn't have John Wayne. Exactly. You would show me a movie. We don't have to watch the movie. You can just show me on the IMDb. You would show me a movie that doesn't have John Wayne. Well, the man died, I think, in the 60s, in the 1960s or 70s. 70s. Yeah, he died before most of us were born, maybe, or some of us were born. And so have there been movies made since he died? Yeah, so we can clearly find something. So the way I would disprove an all statement, so to disprove this statement, I would say some movies do not have John Wayne. And there you go. This is a very easy statement to disprove. All movies have John Wayne. Obviously, that's not true. I can go for what movies came out. Sonic the Hedgehog came out last year, okay? How many of you saw Sonic the Hedgehog? It was okay. It was entertaining if you like that kind of stuff. That movie didn't have John Wayne in it. You're tempted, let me use a different color. You are going to be tempted to say that the opposite of all A or B is no A or B. But think about this particular case. That would be like saying no movies have John Wayne. So to disprove the statement all movies have John Wayne, you have to try and say no movies have John Wayne. Well, isn't that really difficult to establish? You'd have to go through every single movie and show that it doesn't have John Wayne. But you don't have to go nearly that far. So the opposite of the all A or B statement is actually some A are not B. That's all you got to do. It's a lot simpler to do it that way. So that's how these negations are going to work. So we want to negate a quantified statement. A quantified statement, again, has the word all or no, or some are not. The mechanic told me all piston rings were replaced. I later learned that the mechanic never tells the truth. So what can I conclude? Well, if the sentiment is all piston rings were replaced, we're using the all. So we have to use the negation because the mechanic was actually lying. And the negation then is that some piston rings were not replaced. So some piston rings were not replaced. That is the negation. That is the opposite sentiment. If he tries to tell me all the piston rings in my car were replaced, and I go and I can find one that was not replaced, I've disproven what he said. It could be that there's only one that wasn't replaced, but they did all the other 20 something. I don't know what a piston ring even is, so don't try to hold me to that. I've never, I guess, does it have to do with your cylinders in your engine? So the pistons are the individual cylinders, right? It's another word for it. So a piston ring is something that holds them in place. Something like that. Oh, I'm good. Yeah, so if he tried to tell me all piston rings were replaced, even if I just find one that was not replaced, but the rest were, and he still did a pretty good job, I can still say he's wrong. I can still say, no, you're wrong. Now, I don't know a whole lot about cars. I always wish I did. I've always said this. People are like, Josh, you're good at math. That was me growing up. Josh, you're good at math. You're good at math. You do math. I was like, well, I wish I could be a mechanic. And they say, well, Josh, you're terrible at fixing things. There's two things you're never going to do good, no matter how hard you try. Fix stuff and cook things. You're never going to be able to cook things. So do I still eat SpaghettiOs out of a can to this day? I'm not going to admit that, but yes, I do. I do that. And my girlfriend says I'm disgusting. She looks at me and says, why am I still with you with you eating SpaghettiOs out of that can. I say, well, I bring a lot of other good qualities to the mix. Math? She says that's not enough. And so she left me the other day. That's not true. She didn't leave me. She never leave me. I'm too awesome. Okay. Anyways, that got a little bit weird. Raise your hand if you're like, oh, that's a little weird, Josh. Well, you know what? We got to make things fun in here. We got to make them fun. So that's the basic of statements. We're going to add on to that. We're going to add on to that, as you would expect. And things are going to ramp up a tad bit in difficulty. I thought it was getting a rest. You heard it turn off the projector. Nope, give it a second. It'll warm up, re-warm up, and it will get nice and bright again. Okay. Back to what we were talking about. There it is. We're going to talk about things called compound statements and connectives. So everything we dealt with in the last section there, this is now section 3.2. Everything we dealt with in that section was basically a simple statement, a statement that really just makes one single claim. All poets are writers. That's very simple. What we're going to see is that we can use connectives like the words and, the word or. You can use phrases like if then, if all poets are writers, then William Shakespeare is a writer, something like that. Suddenly you've created a more complicated statement out of that. We call those compound statements. And we use these things called connectives to connect them together. So, like I said, simple statements convey really just one idea. Compound statements, though, will combine multiple statements. We're going to use connectives. Those are going to be our tools for combining multiple statements together. The words and or are the most popular one. How many of you want to hear a really cool hint? Want to hear a really cool hint? In the last section, we talked about the word not. Not. We talked about taking the negation. Technically, that's considered a connective, but because it's still pretty simple to do that, we don't really count it as one. But the word not in logic relates to the concept of the complement from chapter 2, set theory. Remember, we said the complement of set A was everything that set A was not. It was everything outside of set A. What we're going to see then, the word and is going to be the exact analog for the concept of intersection from set theory. The word or is going to be exactly the same as the union from set theory. If then is going to be our concept of the subset from set theory. If and only if is the concept of set equality from set theory. So pretty interesting stuff. By the way, I get 10 cents every time I say full throttle energy drink. I just made 20 cents. This isn't true. Everything I'm about to say is a complete lie to you. But full throttle is a delicious energy drink. It's free and easy to drink. So you guys should drink some. My favorite flavor is the blue agave full throttle, but they don't sell them in 8-packs at the Walmart. Anywho, how many of you are like, you go on a lot of weird tangents, Josh? How many of you believe that? How many of you are not actually going to say it to me, but you think it? Well, there you go. Someone raised their hand. Someone's brave. There we go. We got another one. But see, it's because I like to have fun. Not everything's about just math and stuffy numbers. We got to mix it up a little bit, okay? We got to use a little humor. The only reason I use humor, by the way, or some of you might loosely define as humor because you don't think I'm funny, the only reason I do that is because there's actual educational research that suggests that if I just come up here for an hour, 15 minutes and do math, nonstop, you are all going to get bored out of your mind and you are going to stop paying attention. How many of you would definitely agree with that? Yeah, that's going to happen. I'm not stupid. I have taught and I have done that. I realize if you break it up with humor, even humor that's not at all related to what we're learning about, it kind of helps the flow a little bit and it keeps you engaged and whatnot. So really, I'm just manipulating you into learning by telling you a joke. How many of you like that? How many of you are like, it's okay with me being manipulated if it means that we get a little levity in class? I would agree. Okay, so we're going to start off with and statements. Now, when you say the word and, when you use the word and in English, that word makes you think that you are growing something, that you are allowing more and more things in, and thus it's inclusive. For instance, if I'm inviting kids to my birthday party when I was a kid at school, let's say I'm in the 2nd grade, and I have to invite everybody in the classroom, I'm gonna walk around, I'm gonna say, and Timmy and Susie is invited, and Julie and Spencer. If I keep using the word and, that makes me think that I'm being more inclusive and the list is growing of things that I'm allowing in. In logic, though, that's not quite going to be what it means, but you're going to see that it actually still makes sense. When I use the word and in logic, what I'm really doing is I'm connecting different requirements, or I'm connecting, I can't quite think of the word for it. I'm connecting different requirements for something to come in. So if I say you need to have this and this and this and this, I'm not actually being more inclusive. I'm actually making it really exclusive. I'm making it harder and harder for something to qualify. I'm making it harder and harder for something to qualify. So the word and does not expand anything in logic. It actually limits things. So let's use it. Let's talk about it. If P and Q are two simple statements, the compound statement P and Q is symbolized using this. It's symbolized using that little up arrow. It's the caret key, Shift 6 on a keyboard. P and Q. It looks like a capital A with the middle line deleted. So now I don't have to say P and Q anymore. I can just say P, and then I can use that little caret. So let's think of a couple examples. How many of you have ever been to a bar? Probably been to a bar. I've walked into many bars. Yeah, this is a bad joke. You guys ready? Bad joke alert. Woo! I've walked into many bars, and I ordered a drink at them. Not a literal bar, like a metal bar that you walk into and hurt yourself. That's what you were thinking? How dare you think so little of me? No, yes. If you've ever been to a bar, most bars, especially in Texas, require you to be at least 21, right? They won't even let you in because you have 21 is the drinking age. But there are some bars that will let you in if you're under 21, but at least 18. They put a little Sharpie X on your hand so it immediately tells the bartender you can't serve this person. So you're gonna have to go in and have a Dr. Pepper. So let's think about bars. Let's say P is the statement. You must be at least 21 to get in the bar, to get in. That's a statement because it's going to be true or false for a given bar. It's not true for every bar. But let's say we are at a bar that has that rule. Let's take another statement. You must pay a $10 cover to get in. And maybe you've been to bars that do something like that, or you can understand the concept. So, a really exclusive bar might have you do both. In other words, not only do you have to be at least 21, you also have to pay $10 to even get in the door. In other words, you have to give them $10 for the privilege of buying things from them, which is maybe silly, maybe not. Most bars will charge a $10 cover if there's what? A band playing, if there's live music, because the bar is literally going to use that cover money to pay the band. That's what's going on. So that's why you have to pay for it. And frankly, if there's tons of people wanting to get into that bar, they can charge that cover and they'll get it. So a really exclusive bar might have you do both. In other words, a really exclusive bar might be P and Q. You must both be over 21, and you must also pay a $10 cover to get in. So that's going to limit the number of people who can get in. Now think about a bar that is a little more inclusive. Those rules are lax, and they only require you to meet one of those objectives. So the reason a bar will do that, they'll say, if you're at least 21, come on in, you don't got to pay the cover, because they expect you to go in there and buy drinks. And so they're going to make their money off of you, right? If you're under 21, let's say you're 19, so you're still an adult. If you're under 21, they can't legally serve you alcohol. So then they'll charge you a $10 cover, so they're at least getting something out of you, because otherwise you're going to go in, you're going to order a Dr. Pepper. So there are other bars who will say you just got to be one of those two things. So that is going to be P or Q. We're going to learn that symbol in just a second. So the word or is actually expanding the number of people that are going to qualify for that. The number of people who are either at least 21 or are at least willing to spend $10 to get in. The word or is actually going to be the more inclusive. It's going to be the thing that allows the most in, because you just have to qualify on at least one of those objectives. With the word and, you have to qualify on both, and that makes it harder. So when you're talking about rules for something, the word and actually makes it a more restrictive system, a harder system to get into. What's really interesting, super interesting, is if you go to a bar, let's say you're 25 years old, like I was 6 years ago. Let's say you're 25 years old, and you're willing to give them $10 in cover. Do you have to do it at this second bar? No. In this bar, you don't have to both be over 21 and give them $10. But if you give them $10 and you're 25, are they still going to let you in? Yeah. You didn't have to give them $10, but they're not going to say no, sir. So what we're going to see is for this bar, you have to be one or the other or both. If you're both willing to pay the cover and you're 25, you'll still get in. And so what we're going to see is that the word or in mathematics really translates to and or. You can be one, the other, or both. That's in logic and math what or means. So back to the PowerPoint, back to our little note set. Let's say that we have two statements. The statement P, it's after 5 p.m. Again, that statement might be true or false, but we're just talking about it in theory. Let's say Q is the statement, they are working. Who's they? Who cares? It's still a statement. If you wanted to say the more compound statement, it's after 5 and they're still working. You could literally write P and Q. Ta-da! Very simple. So this up arrow almost, if you will, is our and symbol. If you want to say it's after 5 and they're not working, you would say P and, then you would say not Q, because you're taking the opposite sentiment of Q, because they're not working. And then you would literally symbolize that P and not Q here. So it's really interesting. Some other ways to talk about the word and. If you say P and Q, obviously. If you say P but Q. Now that's interesting. The word but, B-U-T, actually, logically speaking, is just the same as the word and. If you use the word but, though, there's some kind of emphasis you're putting on it, or some kind of, not shock value, but you're creating it. So you might say something like, everybody got A's on the test, but you all cheated. That's not really what happened. But if you use the word but there, you're expressing some kind of shock value that is lost when you translate it into logic. Because really, that statement is the same as saying, everybody got an A on the test and they all cheated. Logically, it's equivalent, but it just kind of loses some of that like, whoa moment. So the word but is another, it's a key word. It's another way of saying and. Yet, everybody cheated on the test, yet they all got F's. P, nevertheless, Q. P, however, Q. You can kind of play around with it like that. There's different words that logically translate to the word and. Now let's talk about the word or. The word and is kind of obvious. We all understand the word and. We all think we understand the word or, but there's two kinds of ors. I visited London or Paris. Well, if you can only visit one of those two cities, then if I say I visited London or Paris, when you use the word or, you're using what's called the exclusive or, meaning it's got to be one or the other. It can't be both. Maybe you don't have enough time to go to both. Maybe you don't have enough money to go to both. So in this context, the word or is exclusive. It's one or the other. However, in logic and in mathematics, if I use the word or and I don't otherwise specify, if I say I visited London or Paris, in logic, that means you could have visited London, or you could have visited Paris, or you could have visited both. You have the time or money or whatever to visit both. So you have to be very careful. The word or really takes on two different meanings almost that are similar but have a distinction. But in math, in mathematics as in logic, the word or is this second case, one or the other or both. Well, we called the and statement. I don't think I used the word. It's not super important. We called the and statement the conjunction. The conjunction. It conjuncts two things. It brings them together. The word or is called the disjunction. Disjunction. Conjunction for and, disjunction for the word or. It is the inclusive or. If I say this or that, it could be both this and that at the same time, or it could be one or the other. And instead of using a caret pointing up, now it's like a caret pointing down. It's just the flip it over. So this is now the word or. This is that bar that lets you in if you're over 21 or you're willing to pay the cover. If you're going to do both, be over 21 and pay the cover, they're definitely going to let you in. But they're not going to let you in any more than they would have if you just did one or the other. But it's an interesting idea. If you're talking about the statements P, the bill receives majority approval. Q, the bill becomes a law. If you want to say the bill receives majority approval or the bill becomes a law, you use P or Q. P, then the disjunction symbol, the V, if you will, capital V, and then Q. If you say the bill receives majority approval or the bill does not become a law, you would say P or not Q. If you say the bill does not receive majority approval or the bill does not become a law, it would be that, not P or not Q. So when you use the not symbol, when you use the tilde, it only applies immediately to the letter right after it, and then it stops. It does not mean this. where you do this part first, then take the negation of it. That's not what it means. The tilde stops at the P. The buck stops here. Again, I can't emphasize enough. Everything we're learning here has a direct analogy in set theory. So everything you've already learned in set theory can help you out here with this material. So let's say P is the statement, you must be at least 21 to get in. Q is the statement, you must pay a $10 cover to get in. So this is chapter 3 logic stuff, logic theory. Let's talk about chapter 2 set theory. We would say A is the set of all people 21 and up. So if you're talking about a set of things, that's going to be a lot of people. It's going to be millions and millions of people if you're talking about the US of A. B can be the set of all people willing to pay a $10 cover. Willing to pay $10 to get into the bar. The exclusive bar requires, basically, it requires P and Q. It requires you to be both 21 and up or pay $10. The exclusive bar requires P and Q. In set theory, what we're going to say is the exclusive bar requires you to be a member of A intersect B. Remember, the intersection is the thing that these two sets have in common. The set of all people 21 and up and the set of all people willing to pay $10 to get in. You got to be in both those things. The intersection inherently is smaller, or usually is smaller. It takes some of the first set, some of the second set, and brings them together. So the and in logic is the same as the intersection from set theory. They're basically identical in truth. How many of you would say that's kind of cool? Yes. Well, remember we defined the intersection in set theory. We used the word and. We said to be in the intersection, you have to be in set A and set B, if we go back to the definition. So that's just another way of saying and. So it is really cool that we have that analogy. Now the more inclusive bar, the one who's willing to let more people in. In logical terms, in P and Q terms, it requires P or Q. It requires you to either be at least 21 or be willing to pay $10. And I misspelled inclusive. In set theory, the inclusive bar requires you to be a member of, now instead of A intersect B, it's A union B. A union B is the set of all people either in set A or set B, or perhaps in both. The inclusive bar then requires you to be in the set of A union B. So the or in logic is the same as union from set theory. They are pretty much the exact same thing, just different expressions of them, different expressions of the same idea. In fact, when we defined the union in set theory, we said A union B is the set of all things in set A or set B or both. That was a straight up definition we used. Okay, so let's go ahead and call it Don't leave just yet. Let me take attendance. Brooklyn. And we can stop.